Hello, we are Group 21 and our project is Multimodal Sarcasm Detection, using audio, video, and text to improve automatic detection of sarcasm. This is our contents. Introduction. Sarcasm detection is a sentiment analysis task which requires understanding of the conversational context. The ironical and metaphorical nature of sarcasm poses a challenge for computer models that try to analyze the sentiment. In this image, the AI bot that is responding to the tweet of an angry customer that is criticizing the service of the airline has completely misunderstood his anger and sarcasm to be literal appreciation. This is why we need sarcasm detection in conversational AI and opinion mining, etc. Previous methods. Previous attempts to detect sarcasm have mostly been unimodal approaches. Speech based systems have used rhosodic features and spectral features to detect sarcasm. NLP systems use context incongruity and deep learning methods in order to detect sarcasm. Embeddings of personality features help in adding context and have also been used in sarcasm detection. However, approaches using visual markers and sarcasm in conversation have been rarely studied. Thus, we aim to detect sarcasm in video segments of dialogues by combining video, text, and audio modalities to derive contextual information. Our dataset. We are using the mustard dataset, which consists of audio-visual utterances annotated with sarcasm labels that have been compiled from popular TV shows like The Friends, The Big Bang Theory, Sarcasm Holics, etc. Each utterance is accompanied by its context, which offers more details about the situation in which the utterance takes place. The dataset consists of 345 sarcastic videos and 6020 non sarcastic videos. This is the methodology that we will be following. The input data, which is the videos of the dialogues from the different shows, is then provided to our feature extraction module, which separates the audio, video, and text and then pre processes them using Librosa for audio, CNNs for video, and BERT for text and extracts the features. These extracted features are then passed to our unsupervised models, and then our supervised models, and the results that we get are analyzed. We'll be able to see all these steps in more detail in our future slides. Let's begin by discussing feature extraction. Feature extraction in text is done using BERT. We begin by tokenizing our text by using NLTK's Puncti library, and then the tokenized output is fed into our BERT model, and then the BERT model outputs the features vectors of size 768. Feature extraction is on audio is done using Librosa library. First, we begin by vocal separation, in which we extract the vocal component from the audio. This helps in removing the laugh tracks in certain video files like that in Friends and Big Bang Theory. The next step is to extract the MFCC, Mel scale spectrogram, and their centroids. All of these features, along with their deltas, are extracted, and then their each file is divided into segments which are of about 512 for each file, and then we average them to get a final feature vector of 268 for each video. To extract the visual features in the video, we use a pre-trained ResNet, and we get a feature vector of size 2048 representing the entire video file. Exploratory data analysis. The main aim behind exploratory data analysis is to understand the distribution of our data and how unbiased it is. We begin by checking the polarity distribution in sarcastic and non-sarcastic comments. We see that in sarcastic comments, they are overly positive, which is likely because we try to sound extremely happy about not so positive things in our sarcastic comments. And whereas the polarity distribution in non-sarcastic statements end up being more neutral, which seems like a very fair distribution. When we plotted the word clouds, we understood that there was no relation between the word and the comment that is being sarcastic. Next, we plotted the distribution statistics of the dataset to see how the sarcastic statements are divided between the different shows, the different actors, etc. Moving on to exploratory data analysis of text, audio, and video. We plot the correlation between the different features, and we see that the features are all highly related. We first have a correlation matrix heat map, and the coefficients plotted as a histogram. We see that the features have a high correlation and hence they can be reduced to a smaller set of features that can still capture the variance in the data. In the graphs on the second row, we have captured how the feature values change between the sarcastic and non-sarcastic data points. Higher the value of this difference, greater is the shift between the two classes. We found some reasonable but not significant shift between the features for these two classes. Feature reduction. We've used two methods for feature reduction. First is most drifted features, and the second is principal component analysis. Most drifted features uses 10-fold cross-validation to choose the top k drifted features, whereas PCA chooses the top 100 components. We noticed that only about 77% of the variance was captured by our first 100 features. Unsupervised or semi-supervised learning. We used Gaussian mixture model and k-means clustering algorithms for our unsupervised or semi-supervised learning module. The semi-supervised learning aspect comes in because we use most drifted features, which uses class labels. Hence, the GMM or k-means with this method of feature selection becomes semi-supervised. However, when we use PCA for feature selection, GMM or k-means remains unsupervised. The performance of these models is evaluated using precision, recall, F-measure, Jacquard coefficient, RAND statistic, Falks-Mallow measure. Supervised learning methods. The problem was set up as a binary classification problem. Given the input video or audio or text or multimodal features, we need to classify the input as either sarcastic or non-sarcastic. We use 5 supervised learning algorithms to develop the model. We have Gaussian namespace, XGBoost, random forest, support vector machines, and deep neural networks. The metrics that we use for evaluation in this case are precision, recall, F1 score, accuracy, and ROC-AAC score. When analyzing the supervised learning, we learned that SPM performed the best. Now, moving on to results and discussion. Feature selection or reduction comparison. Here we compare between most drifted features and PCA as methods for feature selection. From the graph, it's clear that most drifted features outperforms PCA, and this could be because it uses the class labels rather than maximizing the variance, and thus it is able to choose features which are more relevant to our task. In the next step, we will analyze the results from unsupervised or semi-supervised learning. The performance of k-means is slightly better than Gaussian mixture model. Using the most drifted feature selection technique yields much better results than that using PCA. Results from supervised learning. We see that SPM outperforms all our supervised learning models. And this could be because SPM's intrinsic behavior to manage overfitting much better than the other models. Comparing the modalities. From the previous slide, we know that most drifted features is the best feature selection method, and we know that SPM is our best classifier. So we've compared the performance on different modalities only for SPM that uses most drifted features. We see that the combined modalities has a much better performance when compared to the individual modalities. This proves the need for multimodal or for using multiple modalities in the task of sarcasm detection. This is our references, and the next slide contains our team member contributions, followed by some other relevant slides for our presentation. Thank you.